All right.
All right,
So,
Mike. So
can you
just
see
one
everything?
second, Michael, and let me introduce you.
All right, please do.
So now Michael Kirk from Astra, and he's sitting at NASA. We'll talk on big data and the promise of big science. Go ahead, Michael.
All right, thanks, Dean. And now for something slightly, completely different from what Sabrina was talking about. Thanks for having me here. Thanks for giving me a chance to talk about things that I like to think about and share them with you. And so today I'm going to be talking about the big data problem and opportunity of AIA and the promise of big science that it presents. But to kind of bring you back to the very beginning of where this all started for me, it brings me back to a question that Neil Hurlburt posed to me back in 2015. I was out visiting LASP, and he was showing me the stacks of hard drives collecting and serving the AIA data. And he sort of casually tossed off this question, which is, what would you do with the complete AIA archive? Well, that sort of stumped me at the time. I don't remember what I said exactly. Maybe Neil does. But whatever it was sort of a punt because I didn't really have a good answer to that. But as I started to sort of chew over it and think about it over the next few years, the question shifted from what would you do to what could you do, which is slightly different. So let me just explain a little bit about what I'm thinking about in terms of what could you do. So the scale of the AIA archive, everybody knows it's large. We have a lot of data, a lot of high resolution data. Currently, it stands at about 8.7 petabytes of compressed AIA images and products. Those are flat fields and dark images, as well as the level 1 or level 0.5 images. And level 1 database is about a little over 6 petabytes. So uncompressed, this would be about 20 petabytes of space. And so for a diagram, just to kind of get your mind wrapped around it, that's what you see here, the larger circle, the area of that circle there represents the AIA database as it exists now. And for comparisons, there's SECI A, SECI B, and EIT, all with the appropriate amount of area representing their database sizes. So at current state-of-the-art disk speeds, so these are solid-state disks, they can read and write at about 7,000 megabytes per second. So that would take about 14 days to read through all of this data. That doesn't seem so bad. 14 days is pretty good. But actually, that's a really optimized rate, and that's highly optimized for their glossy brochure. So in reality, it's closer to about 500 megabytes per second, so about 200 days to read through the entire AIA archive. Again, that isn't so bad. However, size isn't the only issue. The issue is that there's over 230 million level 1 images to look at. And so it's not just about the quantity of data, it's also the number of images and the variety of data to explore. That led me to the need for data science. And actually, this represents the outline of the rest of the talk, which is this intersection of the algorithms to use, the data we have, the computing power we can leverage, and our solar physics that we want to know. And at the intersection of this all, a group at Goddard, we came up with the term helioanalytics to represent this small little square right in the center, which is the intersection of all these different pieces. And the issue about helioanalytics is that it takes collaboration, coordination between all of these different parts working together to really start asking and answering some of the biggest questions. So that's what I'm going to do for the rest of my time is I'm going to walk through each one of these sections, talk a little bit about the current state of the art, some early successes, and then I'll finish up sort of talking about what we've done well, what our opportunities for growth are, and then I'll give you my vision into my crystal ball and talk about what the near future is going to look like as we move forward into this brave new world of helioanalytics. So first, data. Of course, we have data. Most people on this call have at least have worked with AIA data, if not actually, done a lot of processing themselves, since we have a lot of data experts here for AIA. But I just wanted to sort of iterate this sort of data problem in a new way to kind of get you to start thinking at scale. So AIA is served out from the JSOC as a level 0.5 data product, which means that for most scientific studies that an AIA prep routine needs to be run first on the images before you want to go ahead and answer your science question. And this AIA prep entails a translation of the image, a resize, a rotate of those images to get everything nicely lined up and on the same plate scale and the same scale. There can also be some degradation corrections thrown in there as well. In addition, there's a lot of science that is interested in doing a point spread function removal. Mark Chung was mentioning it in the chat. And so this idea of removing the point spread function from the image is becoming more and more critical to answering questions. Okay, so it's fine doing it with 1 or 2 images on your desktop. Maybe you have several hundred images and you want to process it. Running that in a series fashion on your desktop isn't it a big deal? What if you wanted to run the entire AIA archive? Well, now all of a sudden that becomes a very big deal and becomes a big challenge. So what I'm showcasing here, the little animated GIF, is a project that Will Barnes has been working on for the last few years, is incorporating a software tool called Dask to do a distributed computing approach for this AIA prep. And so using this Dask approach, you can now leverage your entire system that you're working on to actually do that AIA prep, the data prep step itself. And so whether that's just the 4 cores you have on your laptop, or the thousands of cores or tens of thousands of GPU cores that you might have on a HPC environment. And so this type of software is incredibly scalable so that you can actually prep your data as you need to in batch amounts. So at Goddard, we're running a little a test pilot project of looking at 1 month of high resolution AIA data, as in all of the images available for 1 month, and using a hybrid CPU GPU cluster in this sort of format. And we're getting at about 0.5 seconds to prep each image. That's of course not optimized yet, but that's getting there, because nominally each new image from SDO AIA comes in at about 1.3 seconds. So if we can get well under that 1.3 benchmark, we might actually have a chance for catching up, so to speak, by being able to serve new data in a fully prepped way in real time, that you can just ship it out the door as a level 2 data product or as a level 0.5 data product, depending on what your science needs. So this leads me to the compute architecture, like that second piece of the puzzle, computation. So cloud computing resources are becoming more available and more popular. However, there's this large gap that exists between your personal desktop or laptop, with what you're used to prototyping software and new code on, and the full HPC environment or a cloud environment where there are effectively infinite resources, as much money as you can afford to spend. And so data science workstations are coming in to fill this gap between these two computing environments, because they're very different in terms of the way you interact with them and the way you actually engage with them yourselves, especially when it comes to GPUs, graphics processing units. Because as you want to utilize your GPUs in your code, you don't want to just have a single GPU to operate on. You need to have multiple GPUs to understand how your code can be parsed out into different jobs and different sections and run simultaneously. So what I'm showing here is a picture of the Z8, HP Z8 workstation that Raphael Attier and Benoit Tremblay had been using to run their DeepValue code on. And this has become a critical component of that investigation, because without a reasonably high performance desktop computer workstation that you can use as like a large sandbox, moving up into an HPC environment is difficult. The good news is that solid state storage is now relatively affordable. So the super fast storage is now available for purchase in mass. You can get up to about 100 terabytes in size by coming up with an NVMe SSD RAID. I put affordable in quotes because I mean, it's still going to cost you several $100,000, but it's at least doable now. However, the really interesting thing, though, is that on-premise petabyte-sized storage systems are not only imaginable, you can actually buy them. You can get a 1.6 petabyte RAID storage for less than 100K right now, today. So it's not hard to imagine a time in the near future that at your university, at your research institution, that you could host the entire AIA database yourself at your institution. The downside is that many of these legacy HPC environments that exist at universities, exist at Goddard, exist many other places, are not well suited for this type of analysis, because it's sort of we're going in the opposite direction of the data that they're used to using. So in typical HPC environments, you're using models and you're developing these things, and so you're taking a code and producing a lot of data. Here we're taking a vast amount of data and reducing it down into a very small amount, and HPC environments are not well suited for that. So next piece is algorithms. So there are two major types of machine learning algorithms that are really coming into their own and starting to be utilized. And machine learning algorithms are more accessible than ever. I mean, especially with Python, with PyTorch and TensorFlow, but in addition to that, with MATLAB toolboxes with IDL, machine learning algorithms are available and are ready to use out of the box for you today. However, it's how to use them effectively and efficiently is still an ongoing process. So the reason why everybody is very interested in these machine learning algorithms is that once one of these models is trained with data, and I'll explain a little bit in a bit what training means, but once one of these models is trained, it's very efficient to apply it to a vast amount of data. It is extremely computationally efficient to run through terabytes, petabytes of images to actually apply these things. So there's two types I'm showcasing here. Up top is a supervised learning, which is a UNet LSTM framework. I'm not going to explain that, but happy to answer questions about UNet LSTM. This network has essentially been trained to replicate some of the labels that have been stored in the HEC. So this is specifically SPOCA labels. We've used the sunspot labels, active region labels, and coronal hole labels. What you're seeing here is the active region labels. We've trained this algorithm to be able to reproduce those labels on new data, and that's what you're seeing here is those reproduced labels. Shay is actually going to talk a little bit later on today about other applications using HMI of supervised machine learning. The other side of machine learning, and this is where the really interesting stuff happens, and I'll talk a little bit more on why I think it's interesting later, is the unsupervised learning. And this is where you don't have labels, you are into a new data environment. And highlighting a early result from a work that Benoit Tremblay has led is using a WNet to actually break apart a synoptic image, EUV images, into its individual classes of components. And so this is excellent for, excellent for looking at high resolution data and parceling it out. So the last bit is scientific questions. How do we actually reframe our scientific questions in order to be better use of the data? And so I want to walk through an example that we recently ran, Raphael Ate and I recently ran, which is, okay, so here's an AIA image. That's how you download it and look at it. But it has been despiked, meaning that all of the AIA cosmic rays have been removed. If we add all of those back in over a day, they look something closer to this on the screen, which is just sort of chaos. So it's good that they've been removed. However, this presents an interesting opportunity, which says, let's say, why don't we just select places where AIA has 3 consistent hits between different wavelengths of an AIA or one of these cosmic ray spikes, one of these AIA spikes. So consistent, I mean at the same time or within 12 seconds of each other, and at the same location on the CCD. So if we just limit to 3 coincident hits, we've eliminated most of these spikes. Well, let's go a little bit further and say, let's say that in 5 different wavelengths that AIA takes, we need to have one of these spikes hit at the same location and at the same time. What we get then is just what's highlighted in red. And that presents a very new, interesting paradigm to search in, because now we have single pixel events that are dynamic and erupting. And then you can go on and look at some of the physics underneath and identify whether they're jets or whether they're some other small eruptions, or what's very interesting to me are events that are happening off the disk, and like what is actually happening out there where you get a tiny bright pixel. Okay, so what are we doing well? Just to walk through, AIA is a great data set to work with. There are curated data sets being built right now. Galvez and the GSU DM Lab are great examples of curated data sets that are smooth and ready for you to jump in and work on. There's new software resources being developed all the time for use in HPC environments with AIA, including NDCube, CuPy, Dask, Cython. All these codes are really user-friendly and ready to use. Where can we do better? Well, the major issue that I've found is that the data and the computing environments are not associated with each other right now, which means you're constantly moving data to the computing environment or the computing environment to the data. And that makes that's a major barrier for actually implementing a lot of these new studies. Additionally, we need to be able to reshape some of the current science questions into data science questions to actually target what the possibilities and capabilities of AIA are, the true capabilities. Again, additionally, we also need to integrate ethical AI to clarify exactly what ML can do. And that's ethical, I mean, it needs to be reproducible, reliable, transparent. You need to understand what the inputs and the outputs mean, because without those sorts of ethics and reproducibility, machine learning can just sort of go off and predict anything it wants. And then lastly, we need to consistently develop and support robust label archives to host the labels and the metadata and the data all at the same repository so that they're accessible, so that some of these new machine learning tools can be readily used. Just in the last few minutes, I'll paint a quick view of my ideal future. So I think some of these machine learning models will be ready for you to download and use on your desktop. So you can just download an AIA image, for example, download the model and label everything instantaneously. With this will come long-term statistics for solar features, like how often do loops erupt, or what does a typical coronal hole look like? How long does it last? However, the discovery science is really in the realm of unsupervised learning. These high-dimensional relationships that we have never probed and we've never observed before, that is where some real true discovery exists. Of course, people will misuse and abuse this, especially when it comes to predictions. Any sort of AI or ML results will be stretched beyond what they actually mean. So that's why some ethical reproducibility is needed. Well-curated data sets are going to continue to have immense value and will grow in their value, because newly graduated heliophysicists will also be data scientists at the same time. These two fields are going to be knit together. So data processing pipelines are really going to have a future of machine learning fully integrated. And that's from everything from onboard processing on the instrument all the way through data prep, all the way to your analysis. All right, well, thank you very much. I'd be happy to take a few questions, and I like thinking about this stuff, so I'm happy to talk with you more further elsewhere too.
Thanks so much, Michael. That was great. I've been monitoring the chat, and mostly it's about things like what level of data should be hosted or used, and should it be raw data level 0.5, higher order? I'm not sure that there's specifically questions for you about that, but I don't know, maybe you have some thoughts on that you didn't specifically touch on yet in your talk about, you know, what are the appropriate levels that make things like machine learning, you know, work well.
Yeah, those are really good questions, because there isn't a clear answer, and it kind of comes down to the science that you're wanting to do. If you're wanting to do something like supervised machine learning, like find, let's say, loop oscillations, find all the loop oscillations that ever existed in the AIA database, then you need something very highly stable and highly curated. If you are not as interested in that and you're interested in other trends or other relationships, you might not need that sort of processing level. And it might actually be detrimental. Like, for example, the spikes, the AIA spikes, those were removed from the level 0.5 data, but I wanted to use them. So it isn't a one-size-fits-all solution, and that's really the hard part.
Gotcha, thanks. I'm not seeing specific questions pop up right now, but I'm sure there'll be plenty of discussions on this after the talk. Oh, I see Mark's hand is up. We have 1 minute left, Mark. I don't know.
We have to unmute Mark specifically if we can find him.
Okay, there we go.
Hi, Michael. Thanks for your talk, and it generated a lot of discussion. Obviously, many people care about this topic that you raised, and there were all these questions about curated data sets versus lower level data. And I think it's good that we have so many people thinking about it. I think what we need to recognize is that most of us are not using the compute capabilities of our machines and what NASA offers to the full capacity, and we need more people trained in doing so. And by having more people able to marshal the computing resources available, then we can come up with really scalable solutions. That's all.
Absolutely. I 100% agree. And so the tools and the know-how are being built now, but they're critical now. They're going to be more critical in the future. I couldn't agree more, Mark. Thanks.
Thanks. And thanks again, Michael. We are